Right now, a robot is learning to fold laundry by watching humans do it thousands of times. Another one is practicing how to walk upstairs by falling down those same stairs over and over again. And somewhere in a lab, a machine is trying to understand why we smile when we re-happy and frown when we re-sad. These aren't science fiction characters. These are real humanoid robots, and they're getting closer to moving, thinking, and working alongside us every single day. But here's what most people don't know. Making a robot that looks human is actually the easy part. The real challenge is teaching a machine to do things that you and I do and even think about, like catching a ball or opening a door without ripping it off its hinges. Before we continue, what's one human ability you think robots will never be able to truly copy? Write it in the comments section of the video so we can discuss it together. Let's start with the most basic question. Why do we even build robots that look like humans? The answer is surprisingly simple. Our entire world is designed for human bodies. Stairs, door handles, car seats, keyboards, everything. So if we want robots to work in our spaces without rebuilding everything from scratch, they need to have our shape, 2 arms, 2 legs, 2 hands. But copying the human form means copying one of the most complicated machines in nature. Your body has over 600 muscles and 200 bones working together in perfect harmony. A humanoid robot needs to recreate that with motors, gears, and metal. Here's where it gets interesting. Inside each joint of a humanoid robot, there's usually an electric motor connected to something called an actuator. Think of actuators as artificial muscles. When the robot's computer brain sends a signal, these actuators contract or extend, making the robot move. But unlike your muscles, which can gently adjust their force in milliseconds, early robot actuators were either on or off, strong or weak with nothing in between. This made robots move like, well, robots. Stiff, jerky, and awkward. Modern humanoid robots solve this with something called force feedback sensors. These sensors constantly measure how much pressure the robot is applying. So when a humanoid robot picks up an egg, it knows to use just enough grip to hold it without crushing it. When it shakes your hand, it matches your pressure instead of breaking your fingers. But moving smoothly is only half the battle. The other half is balance. You probably don't realize this, but right now, as you're standing or sitting, your body is making hundreds of tiny adjustments every second to keep you from falling over. Your inner ear senses which way is up. Your eyes track the horizon. Your feet feel the ground beneath you. Your brain processes all of this instantly. Humanoid robots need to do the same thing artificially. They use devices called gyroscopes and accelerometers, the same technology in your smartphone that knows when you tilt it. These sensors tell the robot's computer which way it's leaning. Then the computer calculates which motors need to activate and by how much to correct the balance. All of this happens dozens of times per second. When you see a humanoid robot walking, it's not just moving its legs forward. It's constantly catching itself from falling, one step at a time. Now let's talk about the brain. A humanoid robot's computer brain is usually located in its chest or back, where it's protected. This computer runs complex software that controls everything, from walking patterns to object recognition. But here's the wild part. Teaching a robot to walk isn't like programming a calculator. You can't just write step-by-step instructions because every surface is different. Every obstacle is unique. Engineers use something called machine learning. They let the robot try to walk thousands of times in a simulation, failing over and over. Each time it falls, the software adjusts slightly. Eventually, the robot's AI learns what works and what doesn't. Similar to how a baby learns to walk through trial and error, except the robot can practice 10,000 times in a single day inside a computer simulation. Vision is another massive challenge. Humanoid robots use cameras as eyes, usually placed where human eyes would be. But seeing isn't the same as understanding. When you look at a chair, you instantly know it's a chair, that you can sit on it, that it's probably sturdy enough to hold your weight. A robot sees millions of pixels. To make sense of those pixels, the robot uses artificial intelligence trained on millions of images. The AI has learned to recognize patterns. These pixels arranged this way usually mean chair. These patterns mean door. These mean human face. But understanding three-dimensional space is even harder. How far away is that chair? Is it moving toward me or away from me? Many humanoid robots now use depth sensors or multiple cameras that work together like human eyes, calculating distance by comparing the slightly different images each camera sees. Then there are the hands. Human hands are absurdly complex. 27 bones, 34 muscles, and the ability to perform both powerful grips and delicate pinches. Some humanoid robots have simplified hands with just 3 or 4 fingers. Others try to copy human hands exactly, with individual motors for each finger joint. The most advanced robot hands have touch sensors on every fingertip, detecting not just pressure but also texture and temperature. This lets them tell the difference between glass and plastic, between something hot and something cold. But even with all these sensors, tying a shoelace or threading a needle remains incredibly difficult for robots. These tasks require not just dexterity, but an intuitive understanding of materials and forces that humans develop over years of touching and manipulating objects. Power is another real problem. Your body runs on food, which is incredibly energy dense. Humanoid robot runs on batteries, which are heavy and drain quickly. Most humanoid robots can only operate for 1 to 3 hours before needing to recharge. Some are tethered to power sources, but that defeats the purpose of having a mobile robot. Engineers are constantly working on better batteries and more efficient motors. Some experimental robots even use artificial muscles made from materials that contract when electricity passes through them, using far less power than traditional motors. Communication is the final piece. Humanoid robot working alongside humans needs to understand commands and express its own status. Some use voice recognition to understand spoken words. Others watch for hand gestures or read text on screens. The robot also needs to communicate back. Some have screens for faces that display simple emotions or information. Others use LED lights or sounds. The most advanced ones can generate speech that sounds almost human. But understanding context remains difficult. If you say "grab that" while pointing, a human instantly knows what you mean. A robot needs to process your words, identify your pointing gesture, track your finger direction, identify objects in that direction, and determine which one you probably meant. All of this happens in the background while trying not to crash into anything. So when you see videos of humanoid robots walking through warehouses or doing backflips, remember you're watching thousands of sensors, dozens of motors, and millions of lines of code working together in real time. You're watching machines attempt something that took nature millions of years to perfect: the human body. And while they're not quite there yet, every year they get a little bit closer. The robots learning to fold your laundry, walking up those stairs, and trying to understand your smile are all part of humanity's attempt to create helpful partners that can exist in our world without us having to redesign everything for them. That's how humanoid robots work. What's the first job you'd want a humanoid robot to do in your home, and why? Write down your reply or any questions you have in the details section of the video. Like and subscribe for similar upcoming AI content. Then watch the next video that will appear in front of you soon.